We're still working on the same objective from yesterday. But I want to start with this. I've spent so much time putting in late homework over this last week. And when we came back, I wanted you to get to the point where it felt like kind of normal. I know it's not normal. You look next to you and you see seats empty and all that kind of stuff. But I wanted to give everybody a chance to get back into the groove of school. And so one of the things that I decided to do was to give full credit for any assignments that are turned in before the test. But I realized this last week that that's enabling some really bad habits on my part. It's allowing some people to think it's okay to go 6 days and then do all 6 assignments at one time. That's not how our brain learns math. Our brain learns math in chunks. That's the best way to learn it. It's the best way to be successful. And so starting now, I'm going back to the syllabus. And if you turn it in on time, it's all corrected, everything looks good, you get the 2. If you turn it in late, then you get a 1. You get half credit for it. Because we have to get back into, we are back in school. Let's try and at least act like it's kind of normal again and go through it that way. And then the other thing we have to start doing is I have to start talking about the objectives more. I was going to wait until after spring break to really hit this hard, but everybody received one of these yellow lesson objectives. And these are the pieces that tell us when the juniors take the MCAs, this is what they're expected to know. This is the standards that are on there. And so I want to make sure that you know we're covering things that are definitely things you're going to be tested on. So for 7A from section 7.1, we have I can model exponential growth and decay. And we did some graphing already, so we're getting there. But what we have to do with model is also be able to work with word problems. And so that's the piece that we have to get to today, starting I feel like we did that one. We didn't do that one? Okay. So, oh, that's right. The bell was going to ring, and we did the growth and decay and the percentage of growth or decay. All right. So, yep, we're right here. Thank you. So, example 3 says, you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So I realized, well, the hope is I put the money in and I make more money. So I want to pick the formula that had the plus in it. That's the one I want, because I'm hoping to have more money when I'm done. And the initial amount goes in for lowercase a. So how much money did you put in? $1,000. What's our interest rate as a decimal? 0.05. This one was 5%. I think some of you are already doing the exponent, aren't you? And yeah, 6 years. And again, we can do the dollar plus a nickel in our head, so we don't have to punch it in with a plus in there. So we need 1,000. And then 1.05 to the 6th. So $1,340.10. Even though, like I talked about yesterday, we know the bank would just give us 9 cents, but $13.40.10. Not bad. In fact, totally out of the realm of possibilities right now. You know, if you're able to find some way to invest your money and make 3% right now, that's the highest you'll be able to go. That's it. Again, the trade-off is if that savings account is giving you lower money for your return, inflation is supposed to be lower, which means that you don't have to pay $5 for a loaf of bread, you know. So the trade-off, it just goes hand in hand. And it's all economic.
So what's the normal interest rate like before COVID?
You know what, in my lifetime, I think the highest I've ever seen is 4%. if you talk to older Americans, my father-in-law has passed, but he always used to talk about how when they got their house, they weren't sure they were going to be able to make their house payments every month because it was such a stretch for them. And so we asked, well, how much were your house payments? They were $113. I don't know if you guys have talked to your parents about their house payments, but in Elk River, you're probably looking at $1,500 for a house payment every month on average. So they lived at a different time. They lived in a time of war, and things were very, very different. The dollar did not go as far as it does today. So we want to see how does all of this fit. And we've got some more examples here so that we can actually do the modeling objective that we had. And it says the populations of 3 neighboring towns and their growth or decay rates are listed below. Find the populations after 10 years. So I'm looking to see, hey, is it going up? Is it going down? Because that'll tell me which of my formulas I should use. And we have Cedarville that was at 47,162 people, and it had 2% growth. I should be using my plus formula. So it started with 47,162. And I know it's going to be 1 plus something. So 2% is a decimal. What's going to go in those parentheses? All right, you're already doing these, aren't you? That's why you're not talking to me. I'm going to take that as a good thing. So there's my first model, and I'm going to wait and punch them all in at one time so that the computer doesn't feel all stressed out because I'm trying to do 2 things at once. Now, Peter's Land, that one is decay. So we've got 39,650 times, and we would want to take 1 minus, and then we have to be very careful, 0.031. So 0.969. And then we have McD City, which is experiencing some growth, so we'll use the formula with a plus, 58,975, 1.0235 to the 10th. So let's see, I'll put S for Cedarville, P for Peters Land, and M for McD City. And since it's population and it's people, you can't have a half a person. We'll just have to round to the nearest person. So, because I can't see my numbers over there, I will use my notes. 47,162, parentheses, 1.02. to the 10th. 57,490 people in Cedarville. 39,650, parentheses, 0.969 to the 10th. It was supposed to go down because this one was decreasing, so 28,939, rounding to the nearest person. And then 58,975, 1.0235 to the 10th. 603,000. Oh, thank you. That was multiplication. To the, I don't know how I hit multiplication. That's 2 buttons down, for goodness sake. Thanks for letting me know. 74,395. So, 57,490. $28,939 and 74,395. So one of the things that we had in a little box yesterday, pardon me, was population growth. Absolutely. This is a really, really good model to use when you're talking about population growth. Now, when will the population of Cedarville reach 65,000? Use a graph or a table. Those numbers are important. When cities are planning, they have to figure out, okay, how much water do we have for everybody? You know, how are we going to make this sewer system work in the wastewater treatment plant that we have? Do we have to build another one of those? So they have to make projections about when they think that's going to happen. And then they have to hope things stay the same, which they usually don't. But here's what we know. Our model for Cedarville was right here. Except the 10. We don't want the 10. We want to know how many years is this going to take. So I'm going to put an X there because that's what it comes up as on our calculator. And I want to know, when is this going to be equal to 65,000? Which reminds me, Henry was nice enough to email me last night. Problem number 32, you had to wait until you learned this in order to do it. So some of you maybe had to watch the FAQ on that one. Sorry. I did reorder it now so that it's on day 2's assignment instead of day 1's. But this is what you had to do for number 32. And if you're thinking, okay, I'll divide both sides by 47,162, but then what do I do? Because I don't know how to get to this variable yet. I've never done that, where I have a power that's unknown. Well, we're not going to know for a while, because that involves logarithms. Has anybody had to use logarithms in their science classes yet? Okay, so we don't know how to do it now. Now, that doesn't mean we give up, because remember, 2 rules in math. We never give up, and there's no crying in math. Those are important. What we're going to do is we're going to let the calculator tell us this. We're going to put this in as y sub 1, and this in as y sub 2, and we're going to see where they intersect, because we've done that before. We can do that. It's not a big deal. So, if you do have your own calculator, go ahead and grab it. If you don't, just watch me doing it up here. You'll be just fine. We've done this before. So let's see, those numbers again were 47,162. I'll hit that it's approved so that everything goes through smoothly for you.
Thank you.
Yep. Have a great weekend. Hang in there, computer. I'll be right back. Don't have a fit. There we go. Four, 7, 1, 6, 2. Oops, I need to graph that. .02 to the x. And they wanted to know 65,000. So the most important part of this one is going to be the window. So I look at the numbers. It started at 47,162. We found it after 10 years, and after 10 years it was 57,490. So I think maybe if we give it another 10 years, 20 years, maybe we'll be able to see it. So 0 to 20. But my y's, I need some room, because I have to be able to see 65,000. So maybe I'll go with just randomly 80,000. I was thinking about 100,000. It won't make any difference. We should be able to see it. So we hit graph. They're hitting each other. We need to wake up Blinky. Blinky needs to tell us where that is. How do you wake up Blinky? Second trace. And Blinky, we're using number 5, intersection. Bing, bang, boom. A little over 16 years, Blinky says. That's when this is going to happen. We'll go with 16.2 years. So, we don't know logarithms. We have to let Blinky help us out. Y sub 1, Y sub 2, where do they hit? And we go from there. Blinky, the pet cursor. We use the graphing calculator. That's what it's there for. Now, we still have to be able to model word problems, word situations. And here's another one. That is an Iberian lynx. And every year I worry about these creatures and I check to see what the population is. So I'll talk about that in a little bit. Exponential functions are often discrete. Discrete math means countable. You can't have a half a person. You can't have a third of a dog. You know, those types of things make absolutely no sense. So really when we graph them, we should think of them as dots, not necessarily as lines. But if we're going to use the graphing calculator, we want to see where they hit. So we make lines instead. To model a discrete situation using an exponential function of the form y equals a times b to the x, you need to find the growth or decay factor. I mean, that's your base. You need that. That's b. If you know the y values for two consecutive x values, which means like each year or each century, whatever it may be, we can find the rate of change r by doing this. Take the new minus the old and divide it by the old. New minus the old and divide it by the old. Because what we're trying to do is compare it to what it was when we first started. And then we can put that into our 1 plus or 1 minus, depending on if it's an increase or a decrease. So this little Iberian lynx over here, we're going to write a model for this one. It's an endangered species, which means they're almost gone. The table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? Use the general form, y equals a times b to the x, and a times 1 plus r to the x, but in this case this is decreasing, so we'd actually use the 1 minus r formula. So first things first, it says let's talk about the variables that we have here. And I look over at the table and I'm very concerned because in 2003 there were only 150 of the Iberian lynx. And in 2004 it was already down to 120. So in just 1 year they lost 30 Iberian lynx. As I've looked up the research, because I know there's lots of animal lovers out there just like me, what happened was they had sprayed the countryside of Spain and Portugal with weed killers and things like that, and it killed off all the rabbits. Well, what do you suppose an Iberian lynx eats? Rabbits. So many of the Iberian lynx had died of starvation. And they did realize that they were running low, and they did something about it. And so now they're over 400. So it doesn't look good, but it's better than it was. And that's because whenever you get in a situation like that, there's always inbreeding, and then defects end up starting to happen. But that's just how it goes. So define the variables here. We are going to use years as our x. And now it's up to us if we want to say, well, let's have a starting year or not. And I really do prefer that. I don't like having 2000s in the situation for my x variable, my power. So let's do years since 2003. And y is going to be the number of Iberian lynx. Well, if it's going to be y equals a times b to the x, we better figure out what all these good things are. And here's where they're helping us remember how we find b. We take new, 120, minus old, 150, and we divide it by old. Back when you were probably in the 7th grade, that's how you figured out percentage of change. New minus old over old. So that's going to be negative 30 over 150, which if we wanted to just leave it as a fraction, we could do negative 1/5, but most of the time what we'll see happen is they'll change it to decimals for word problems. So 1/5 is the same thing as 2/10. So we have negative 0.2. All right, now we need b. b comes from taking that 1 plus r and realizing we're actually going to be putting a negative 0.2 in here since it's going down. Now, 0.2, what is that as a percentage so we can get our heads around what's happening here? They're losing 20% of these links every year if this continues. So 1 plus a negative 0.2 would be they're keeping 80%. So there are 80% of the links that are surviving. So now we need our model. Y equals, and A is always the initial. What did it start at? So what was our starting year? What was the population of the links? We found B. They're keeping 80% of them. And we want to know, I'll leave it X. Usually we use T for time, because this is going to be in years, but we'll use X because that's what the calculator uses. So there's our model. And it says use the model to find the population in 2014. So 2014, and our 0 year was 2003. How many years passed between 2003 and 2014? 11. So we're going to want to know what's going to happen when x equals 11. So we could just put an 11 in here and just punch that in. Or we could put this in as a graph and then use the table to see what's happening with the Iberian links. Let's do that both ways. So we've got 150, 0.8, or 0.8, and I'm punching in 0.08 there. And we want to know after 11 years. 13 links, rounding to the nearest links. But let's say, because I'm an animal lover, I really wanted to see what's going to happen with this. So we had our 150 to start with. And now I can use the table to see what using this formula says is going to happen to these links. So there's our 11 years with the 12.885. And we're getting to things that would round down to 0. So after about 25 years, they thought the links would be gone if they continued along that pattern of destruction. Like I said, they have about 400 of them now, but they're really worried because well, it's going to happen with dogs too. I think I talked about this with my first semester kids. They think within the next 40 years, breeds like German Shepherds will be gone because of all the horrible medical things that are happening with German Shepherds right now. And when you breed animals that have mistakes in their bodies, you get animals that have worse mistakes. So that's going to happen with the links as well. 5A says for that model that we just used, what would be the population in 2020? That would have been last year. How many years passed from 2003 to 2020? So I still have my table up there. Let me go back to 17 years. If things had continued, 3. There would have been 3 links. Now B is an interesting question because it says if you graph that model, which we did, would it ever cross the x-axis? Would it ever actually get to 0? Right? It'd be like an asymptote for us. So for our graph, it would be no. In reality, the answer is yes, but our graph, no. And that's because we had an asymptote at y equals 0. And exactly, in a word problem, you can't have a negative amount of links, so you can't dip below that, which makes sense that our model is working for it. Like I said, they're concerned, but it's at a little over 400. In fact, the last count they had, I wrote it down, was 475. But they're very concerned. They are doing things about it. So I always think it's kind of like us in the United States and America with the buffalo. You know, once we realized what a mistake was taking place, tried to start saving them. No, no. And I think if people went to, I had never been basically any place outside of Minnesota except for basic training in Texas and that kind of stuff when I was stationed in the military. But I went to Yellowstone. Oh, guys, if you are animal lovers, you've got to go to Yellowstone at some time in your life. We saw grizzlies. Well, they have a list of animals that you can see, and the only animal that we didn't see was a moose. And I thought, that's okay. I saw that moose in Minnesota, you know, as I was growing up. We were leaving the park, and my girls were a little younger. And I said,